Welcome back, everyone. I'm Dr. Chem, and I am absolutely thrilled to have you here for this explainer. Today, we're taking a look at one of the most fundamental, yet completely fascinating, metrics in lipid chemistry, the saponification value determination of oils. Just picture it: golden edible oils pouring smoothly, beautiful lathering soap bars, precise laboratory glassware, and triglyceride molecules dancing right there on the molecular level. We're taking a deep dive into the exact chemical reactions that transform everyday fats and oils into soap through a little something called alkaline hydrolysis. Whether you're into quality control, sniffing out food adulteration, or industrial soap manufacturing, mastering this concept, it's an absolute game changer. So let's grab our safety goggles and step right into the lab.
Here's our map for today's lab tour. We're going to hit saponification and molecular theory, apparatus, reagents and safety, the back titration procedure, calculations and interpretation, and finally, industrial applications.
Okay, Part 1, Saponification and Molecular Theory. Let's dive right into this.
Before we actually start mixing chemicals, we need to lay down the golden rule. The saponification value, or SV for short, is defined as the exact number of milligrams of potassium hydroxide, that's KOH, required to completely saponify exactly 1 gram of fat or oil. Now, you might be wondering, why do we care about this highly specific number? Well, it's because this metric gives us a direct quantitative window into the average molecular weight and the chain length of the fatty acids inside our sample. It is, quite literally, a molecular fingerprint.
Looking at the mechanism here, we've got our primary substrate, a triglyceride molecule. Think of it as a macromolecule with a glycerol backbone holding on to 3 fatty acid chains. Now, when we introduce some heat and 3 molecules of potassium hydroxide, a nucleophilic attack kicks off. The hydroxide ions aggressively attack the ester bonds, snapping them right apart. And the result? The triglyceride splits into a single, solitary molecule of glycerol and 3 potassium salts of fatty acids. And those potassium salts? That is literally what we call soap. It's just a beautifully elegant chemical transformation, right?
Moving right along to Part 2, apparatus, reagents, and safety. Now that we've got the theory down, it's time to set up our virtual laboratory fume hood. Precision really requires the right tools and, of course, strict safety measures. Here's what you're going to need on your bench. For reagents, we're using a 0.5 molar ethanolic potassium hydroxide solution. We use ethanol here, not water, because, well, fats simply don't dissolve in water, and we need everything in a single, happy phase to react properly. We also need a standard 0.5 molar hydrochloric acid solution and a phenolphthalein indicator to visually track the reaction. For the apparatus side of things, a 250 milliliter conical flask, a precision burette, and a reflux condenser are your essentials. And finally, and I cannot stress this enough, safety gear. We are handling highly corrosive bases and acids, and we're literally boiling alcohol. So heavy-duty gloves, a lab coat, and safety goggles, absolutely strictly non-negotiable.
All right, Part 3, the back titration procedure. Let's see how this all builds together.
It's time for the physical lab bench work. We're going to perform what's known as a back titration. Let's walk through this step by step. First up, we accurately weigh about 1.5 to 2 grams of our fully dried and filtered oil sample straight into our conical flask. Step 2, we add a measured excess of our ethanolic KOH, exactly 25 milliliters. We use an excess to ensure that every single triglyceride is totally broken down. No stragglers. Step 3, we attach our reflux condenser and heat the whole mixture over a water bath for roughly 30 to 60 minutes. That reflux condenser is absolutely crucial here, guys. It cools the alcohol vapors and drips them right back down into the flask, which stops our solvent from escaping while keeping the temperature high enough for complete saponification. Once the solution is crystal clear with 0 oily droplets, we let it cool down, pop in our phenolphthalein indicator, which turns the whole thing a brilliant deep pink. And finally, we titrate it with our standard HCl until that pink color totally disappears.
Now, the sheer genius of back titration is highlighted right here. We actually run 2 flasks side by side. Our sample flask has the oil and the KOH, but our blank flask has just the KOH and alcohol, 0 oil. Why do we do this? Think of it like paying for a mystery item with a crisp $100 bill. That $100 bill, that's our blank. It's the total known excess of KOH we started out with. The cashier hands you back your change, right? That change represents the unreacted KOH we measured during our sample titration. So by subtracting the exact change you got back from your original $100 bill, you find out exactly how much that mystery item cost. Or, in our case, exactly how much KOH was actually consumed by the oil.
And that brings us to Part 4, Calculations and Data Interpretation.
We've finished the wet lab work, recorded our burette readings, and cleaned up the bench. Let's transition over to the calculator. And hey, don't let the math overwhelm you. It perfectly mirrors that $100 bill analogy we just talked about. To find the saponification value, we take the volume of acid used for the blank, our $100 bill, and we subtract the volume used for our sample, our change. This simple subtraction gives us the exact volume corresponding to the KOH that was actually consumed. Then, we multiply that by the concentration of our acid to get the actual moles. Finally, as you can see represented by the analytical balance scale, we divide the whole thing by the weight of our oil sample. This standardizes our final number per single gram of oil.
But here's the crucial point. That number, 56.1, where on earth does that come from? Well, 56.1 is the exact molecular weight of potassium hydroxide. By multiplying our moles by 56.1, we anchor the math directly back to the physical chemistry, converting our results straight into milligrams of KOH. It's just so elegant. It beautifully ties our wet lab volumes straight back to the core definition of the saponification value we established at the start.
Part 5. Industrial Applications and Errors. So, now that we have our data, what is it actually telling us? This chart right here brilliantly illustrates the inverse relationship between the saponification value and fatty acid chain length. Take a look at coconut oil, up at the top. It's got a very high SV, around 246 to 260. A high SV means there are a ton of short-chain fatty acids packed into just 1 gram of oil, which naturally require a lot of KOH to break down. Conversely, look down at rapeseed oil. It has a much lower SV of 170 to 179. A low SV means those fatty acid chains are long and heavy, so fewer actual molecules fit into a single gram, meaning it requires way less KOH to neutralize them.
Of course, in the real world, the data is really only as good as the chemist performing the test. A technician can easily miscalculate this value if they stumble into some pretty common forensic pitfalls. For instance, incomplete refluxing. This means the oil hasn't fully saponified yet, which will artificially lower your final result. Then there's inaccurate weighing, or using impure, moisture-heavy alcohol. Both of those will absolutely skew the numbers. And during the titration itself, man, if you blink and miss that razor-sharp pink to colorless endpoint, overshooting by even a couple of drops is going to completely throw off your entire back titration math. So, we've mastered the bench chemistry, but let's shift our focus to the factory floor. Why does this highly precise molecular metric actually matter outside the laboratory? What is the massive economic impact of this one specific chemical analysis?
Believe it or not, the saponification value literally dictates entire global industries. In soap manufacturing, knowing the exact SV is what prevents your soap from turning into a greasy mess, or worse, being heavily caustic and burning the skin. Remember that high SV coconut oil we saw? That makes a hard, highly bubbly, but potentially drying bar of soap. That lower SV olive oil, it yields a softer, highly conditioning, low-lather soap. In cosmetics, this value balances emulsion stability. Over in biodiesel production, it actually predicts how much unwanted soap might accidentally form during fuel processing. And for quality control laboratories, it is a primary forensic tool. If you're a food inspector and someone is secretly cutting expensive dairy fat with a cheap long-chain vegetable oil to save a buck, that resulting lower SV immediately exposes the food fraudsters. It's chemical detective work.
So the next time you look at the soaps in your bathroom, the cooking oils in your kitchen, or the biodiesel powering our transport, I want to leave you with this thought. How might knowing the molecular fingerprint of your oils actually change the products you choose to use every single day? Saponification is just so much more than a routine lab test. It is the invisible chemistry that fundamentally shapes our daily lives. I'm Dr. Chem, and I really hope this cinematic explainer through the world of alkaline hydrolysis has sparked your scientific curiosity today. Keep asking questions, keep experimenting, and I will see you in the next explainer right here at Chemora Studio.